All right, so yesterday we added to our arithmetic. There were 2 equations in arithmetic. There were 3 equations in geometric, and then we did our binomial coefficient and then the individual term. So what is that? 7 formulas. Yesterday we talked about the permutations, which is the factorial, the distinguishable permutations, which is the permutation or the factorial on the top, and then any repeated terms, factorial in the bottom. And then we added in the PNR. Okay, so now we're at that's 10 formulas you need to keep track of. My advice is make sure you're paying attention to them. If you have a formula sheet, that's fine, but make sure you're reviewing them each time. So number 1 says, determine the number of ways in which a computer can randomly generate a pair of distinct integers from 1 to 15 whose sum is 20. So instead of writing them all out, hopefully, start to think about what adds to 20. I can't do any, if the biggest number is 15, then I can do 15 and 5, and I can work my way down. 14 and 6, 13 and 7, 12 and 8, 11 and 9, and then 10 and 10 would not be distinct. So that's what it means by distinct. You can't repeat that integer. So how many ways then can it do it? This would be 1, this would be 2, this would be 3, this would be 4, this would be 5. Now it says generate a pair, okay? So when it pulls a pair of numbers, the order does not matter on that. That is 5 pairs. If it said it pulls one number and then pulls another number, now you're talking that both directions can happen. So yesterday's example was you picked a piece of paper out and then you picked another piece of paper out. So in that case, 15 and 5 would be different than 5 and 15, if that makes sense, okay? This is a pair. So there's 5 total. Number 2 says the telephone numbers in the U.S. have 10 digits. How many different combinations are possible within the area code? So the area code is the first 3 digits. And then the remaining 1, 2, 3, 4, 5, 6, 7 is your local phone number. We use the area code all the time now, but that is the area code, that 954 or 754 or whatever is your area code. Within that, it's asking how many are possible and that a local phone number cannot begin with a 0 or 1. So if we eliminate from the 10 digits 2 digits, this is 8, 10, 10, 10, 10, 10, 1, 10, 1, 2, 3, 4, 5, 6 zeros. So 8 million possibilities. No, it's because it says within the area code. So you assume this is only one. There's only one area code. All right, number 3 says how many different ways can 5 couples pose for a prom picture? Assume the couple stays together. So although this is 10 people, we are considering them to be a pair. There are 5 total objects there, okay? So this is 5 factorial. Which is what? 5 times 4. It's faster to do it this way. 120. Order matters, right? When you're arranging them around, the order matters. Find the number of distinguishable permutations of the letters. Now we're looking for anything that's repeated. W does not repeat. E is there 3 times. K does not repeat. N does not repeat. And D does not repeat. There are 7 total in the beginning. The only one that repeats is E, and it's 3 times. So this would be 7, 6, 5, 4, 3 factorial over 3 factorial. And I get 7 times 6 times 5 times 4. 840. 5 says you can answer any 12 questions from a total of 14 questions on an exam. How many different ways can you select the questions? This is tricky because of the language, right? Is it saying order matters? Are we talking about in what order you can answer them, or how many different ways you can select a total of 12 questions? We know the total is 14, right? We know that's our N. We know the 12 is our R, but it says in how many different ways can you select the questions? So if I go 1, 2, 3, 4, 5, is it a different way if I go 5, 6, 7, 8? Completely different. So the order here matters. Does that make sense? The order matters. So this is a permutation. So this is P, N, R. 14, sorry, in the top, which is N factorial over N minus R factorial. So 14 factorial over 14. This is over 2 factorial. So that's all the way down, 14, 13, 12, all the way down to 2 factorial. On a number this big, so on the one we just talked about, if it was a smaller number, you may not have your calculator, but on a number this big, you would. So if you could use your calculator to do the, like just set it up as your fraction of 14 factorial over 2 factorial. Or 14 factorial divided by 2, because it's the same thing. And it says 4.3589 e to the 10, or E10. What does that mean? Good. This is scientific notation. It's telling you that number is so big that there would be, you would have to move your decimal place 10 times. So you can rewrite this as 4.358 times 10 e to, God bless you, 10 to the 10th power is how that would be written in scientific notation, okay? You would not have something that big on your test, but there are, like I literally separated it into 2 parts. Parts that you can do without your calculator, that are reasonably smaller numbers, and then parts that you need your calculator for. That obviously would be on the calculator part. But even that, God bless you, shouldn't be that big. Yeah. Okay, questions on homework that came up. So hopefully we're starting to understand because the question came up a lot on the phone number one. I think that's number 4. So hopefully everybody understands that now. But this one says any 4-digit numbers can be A, or you wanted B, right? Yeah. The leading digit cannot be 0 and it must be even. So I know it's 4 digits. So instead of assuming that it's all one number, I separate it out into its 4 parts. Normally it would be 10, 10, 10, 10. Because you could go from 0 to 9 for 1 digit. But it says the leading cannot be 0, which means this is now at 9. And the number must be even. So how do you know a number is even or not? Like any number. It's divisible by 2, right? So if I said 1,278, what am I looking at to figure if that's divisible by 2? Just the 8. Doesn't matter if there's 17 digits, if it has 2 digits. You're always looking at the last number and you're trying to see if it's divisible by 2. So what numbers are divisible by 2? 2, 4, 6, 8, 10, which means it ends in a 0, right? How many are there? 5. So the last number is 5. These are any digit in between. So 10 and 10. So this is 4,500. I thought the leading had to be even. No, it says leading can't be 0. And then number must be even. So if it said number must be odd, it's actually the same thing. It could say leading can't be 0 or 1. Like they could say anything they want on those digits.
That makes more sense because I didn't think it had to be like the whole number.
Separate it out. Yep. Same thing with phone number ones. Separate them out. License plates. All those things, separate them out. Treat them as individual spaces. All right. Then 10 says the school locker has a dial clock on which there are 39 numbers from 0 to 38. Find the total number of possible lock combinations when the lock requires a 3-digit sequence of left to right and the numbers can't be repeated. So 3 sequence, like think about your actual lock, right? You go right, you go left, you go right. Each of those can be filled with the numbers from 0 to 38, which means there are 39, 39, and 39 options. And they can be repeated is important. If it said they couldn't be repeated, then you treat this as a factorial. It'd be 39, 38, 37. So that's that 5, 9, 3, 1, 9. All right, we're gonna start 8-6 today. Okay, you're gonna finish it tomorrow, and then this homework assignment is actually due on Monday, and that's the final one of the chapter. So 8-6 is called probability. There's a lot of back and forth between, I would say, calculator and not calculator in here because some of these numbers are going to be huge and some of them are going to be small. But now we're taking those statements that before we were where we just created our sample space, and now we're going to try to find the probability of what we want to get out of it. So first of all, just some vocab. Any happening whose result is uncertain is called an experiment. So an experiment is flipping a coin. An experiment is rolling the die. An experiment is picking a rock out of a bag. Those are all called experiments. The possible results of the experiments are the outcomes. So if I said I'm going to flip a coin, that's the experiment. What's the result of flipping a coin? What could it be? Heads or tails. So heads or tails are the outcomes. The set of all the possible outcomes of the experiment is the sample space. So if I'm listing all the possible outcomes, then that is my sample space. And the sub-collection of a sample space is an event, which is just flipping the coin. The one time or however many times you want it to be, but that one thing, the result of that would be your event. So, for instance, if you have a 6-sided die and it is tossed, the sample space can be represented by the numbers 1 through 6. So 1, 2, 3, 4, 5, 6. For the experiment to be fair, we assume that each of the outcomes is equally likely. So when we go into probability, we assume everything we're trying to get is equal. Whether it's flipping a coin, rolling a die, pulling a rock, whatever it is, we assume that there's no other factor. There's no weighted coins, there's no weighted die. You're assuming that each of them are equally likely. All right, so example 1 says, find the sample space for each of the following. Think outcomes. So if I toss the coin once, what are the possible outcomes? Heads or tails? That is your sample space. What if I flip 2 coins? What are the possibles? What's one outcome that's possible? Heads and heads, then tails and tails, then heads and tails, then tails and heads. Those are all your possible outcomes. And listing all your possible outcomes is your sample space. C says 3 coins are tossed. So what are my possible outcomes? Tails all 3 times. Heads all 3 times. Tails once and heads twice. Tails twice and heads once. Did I get them all? 1, 2, 3, 4, 5, 6, 7. Nope. Tails, tails, tails. Heads, heads, heads. Tails, heads, heads. Tails, tails, heads. Heads, tails, tails. Heads, tails, heads, heads, heads. What didn't I get? Should have gone in an organized fashion. Tails, heads, tails. I'm missing one. 1, 2, 3, 4, 5, 6, 7, 8. Nope, I got them all. Okay, so when you're building the outcomes, obviously you're just trying to see all the different scenarios. There is a strategy, and you're going to learn it, how to figure out how many there are. And that comes from yesterday's stuff. So we talked about if there was to know how many are in my sample space, I would multiply out the number of options from each event. So if I am tossing a coin 3 times, 1, 2, 3. How many possibilities are there the first time? 2. How many possibilities are there the second time? The second time I flip the coin, how many options are there? 2. I flip it the third time. How many options are there then? 2. And so I multiply these together, and I would know there are 8 options. So if you want to know how many there are, then you multiply out the number that are possible each time. All right, so the probability of an event goes one step further and says put what you want over the total sample space, or the number of what you want over the number in the total sample space. All right, so if let's just say the goal is to flip the coin 1 time and to land on heads. What's the probability there? 1 out of 2, right? The one you want over the total amount. Every single probability will fall between 0 and 1. If it is at 0, then it's an impossible event. Like I said, flip the coin. What is the possibility of getting a number 2? Obviously, there's no side that says 2 on a coin, okay? That would be called an impossible event. And then if it's 100% likely, then the probability is 1. So if I said roll the die, and what is the probability of getting a number under 7? Well, every number on that die is under 7, so my probability is 6 out of 6, which ends up being 1. Example 2, 2 coins are tossed. What's the probability that both land heads up? Go back to your sample space. How many possibilities were there if I flipped the coin twice? 4. How many of them had heads and heads? 1. So 1/4, which you will typically leave as a fraction. You could also see this as 0.25. You will never round it unless it literally says 2. All right, B, a card is drawn at random from a standard deck of playing cards. What's the probability that it's an ace? Learn a deck of cards. So there are 4 suits. There are 2 black suits and 2 red suits. The black suits are clubs and spades. The red suits are hearts and diamonds, okay? There are 13 cards of each suit. There's 2, 3, 4, 5, 6, 7, 8, 9, and 10. Those are your numbered cards. Then you have what are called face cards, and a face card literally has a face on it. So the face cards are the jack to the king. And then the ace is by itself, okay? The ace is not a face card, and the ace is not a number card unless it tells you ace is 1. So it'll tell you, is ace low or is ace high? And then we consider it to be in there, okay? Everything else is of the same value. So if it says, what's the probability that it's an ace? How many total cards are there? 52. And how many aces are there? 4, which is 1 over 13. There are going to be questions on cards on your test. You have to understand the deck of cards, okay? So if you've never played with cards before, make it something you do before next week. Jokers do not count. These are like standard decks of cards. All right, mutually exclusive versus not mutually exclusives and or statements. So in the realm of probability, there are 2 major types of statements, and or. An or statement is usually one event in which you're trying to get this or that. You are pulling a card. What is the probability of it being a king or a queen? What is the probability of it being a red card or a heart? Okay, those are your or statements. When it's an and statement, it's completely different. An and statement would be like you're pulling 2 cards. What's the probability you pull a king or a queen and a king? Okay, those are and statements. That comes a little bit later in the notes. The or statements, within the or statement, you have to determine if they are mutually exclusive or not mutually exclusive. What does mutually exclusive mean in like relationships? Do you know what mutually exclusive means? Do you know what exclusive means if you're in a relationship with somebody? No, that's so sad. It means it's just you, right? Mutually exclusive means there's no one else involved, okay? It is just the 2 people that are involved in that relationship. It's the same with probability. Mutually exclusive means that it cannot be to anything outside of those 2 things. So mutually exclusive means jack and a queen. You can't have a card that is both a jack and a queen. Okay? It is red and black. You cannot have a card that is both red and black. Even, odd. The things cannot overlap. Okay? If it's mutually exclusive, then all you do is add the 2 probabilities together. So if it's red and black, obviously that's the whole deck. I would say it's 1/2 plus 1/2. If it's even odd, also, like if I'm flipping a coin, also that's 1. So on a coin, on a die, there are 3 numbers that are even, 3 numbers that are odd. So it'd be 3 over 6 plus 3 over 6. We add those. Mutually not exclusive means it can be both. So that would be like a jack and a heart. A card can be both. And when it can be both, you add the probabilities of each individual one, but then you subtract the probability of the overlap. So, for example, if a card is a 5 or a club, is it possible for there to be a 5 with a club on it? Yes. So I'm going to find the probability that it's a 5. I'm going to add to it the probability that it's a club. And I'm going to subtract from it the probability that is a 5 of clubs. So what's the probability of pulling a 5 from the deck? 1 and 3. Well, let's keep them all the same denominator for now. So go out of the total. 4 out of 52. What's the probability of pulling a club from your suits? How many of each suit? 13. 13 out of 52. Now, how many of those overlap? How many 4 or 5 of clubs are there? 1. Minus 1 out of 52. And that's why we keep the denominators the same. Because now I have to say this is 17 minus 1, so 16 over 52.
Wait, how did you find the 1?
There's only one 5 of clubs. So you're finding what's probably right of the overlap. So this becomes, we can reduce by 2, 8 over 26 or 4 over 13. So every time you start a question, you have to start with, is this an and or? And if it's an or, are they mutually exclusive or not? Those are the 2 questions you're going to ask. Start with this one. One card is selected at random from a standard deck of 52 playing cards. What's the probability that the card is either an ace or a jack? So is this an and or? It's an or, right? It literally says ace or, and it's one event. One event, you want one or the other outcome. So now the question is it mutually exclusive or not? Is it possible for something to be an ace and a jack? No, so these are mutually exclusive. So we're going to find the probability that it's an ace, and we're going to add to it the probability that it's a jack. What's the probability you pull an ace? 4 out of 52. What's the probability you pull a jack? 4 out of 52. So these are both, you can reduce them now, one, because they're both the same. 1 out of 13 or 2/13. You could have an 8 over 52. It'd still give you 2/13. So these will all be simplified fractions. Still good?
We never answer percents, always fractions.
Word problems might answer in percents. So like there are some word problems in this stuff that you might answer in percent, but everything else you'll answer as a fraction. Yeah. All right, example 4. One card is selected at random from a standard deck of 52 playing cards. What's the probability that the card is either a heart or a face card? So first of all, the word or important here. And then we've got heart or face card. Is it possible for it to be both? Yes. So I have to find the probability of the heart plus the probability of the face card minus the probability of the face card that is also a heart. So what's the probability of getting a heart? 1/4 or 13 out of 52? You could have done 1/4 and then seen if the denominators were all the same. How many face cards did we say there are? There's 4 jacks, 4 queens, 4 kings. 12. Minus, how many of those face cards have a heart on them? 3. So I get 25 minus 3, 22 over 52, or 11 out of 26. So if you had gone this route, like this would have been 3 out of 13, and then you would have had to do 3 out of 52. You would have had to find your least common denominator. Wait, yeah. So I would say when you have ones that have 3 parts to it, keep them all over 52 and see if you can reduce it at the end. You have to reduce your answer, but it's easier to do that than to work backwards and find a least common denominator. Questions so far? All right, now we're just gonna get our feet wet on the ands. An and statement is at least 2 events. So usually it's 2 events. It could be more than 2 events, but it is 2 events. And they are either independent or dependent. They are independent when the occurrence of one has no effect on the other. For example, if I roll a die one time and then I roll it a second time, it is the same die. It has the same outcome opportunities. Okay? And for these, you find the probability of each and you multiply them together. So and means multiply, or means add. This would also be, I take a rock out, but I put it back. Okay, I take a sock out of a drawer, but I put it back. So if you are replacing, using replacement to put back your original set, then those would be independent. 2 events are dependent when the occurrence of one does have an effect on the other. For example, there is a box full of rocks. You go grab one, and you're trying to get a red rock out of the multicolored ones. So let's say Bradley goes up for the first one. He grabs a rock out, okay? And then Hayden comes back, and she grabs the second rock. Those events are dependent upon each other because Bradley did not put his rock back. So if there is replacement, it is independent. If there's not replacement, it is dependent. And if it is dependent, we assume you got what you wanted the first time. So you would multiply the probability of the first thing times the probability of the second thing given the first already happened. It's on the next slide, actually. So independent is multiply them out. Dependent is multiply the original probability times the probability of the second thing given the first already happened. So let's say there's 10 pieces of candy in this bin, okay? And I say, come and pick. Sam, come pick a piece of candy. And he wants to get Sour Patch. And let's say they are all 10 different kinds of candy, okay? No, let's say we'll do exactly. There's 2, what are these? Swedish Fish. 2 Sour Patch. 1 Starburst. Let's just do 5. Okay? You're not getting to keep this, just so we're clear. Okay. Sam, I want you to get Sour Patch. You're going to come up here. What's the probability you're getting Sour Patch? 2 out of 5, right? Now, we assume he keeps that. You're not going to keep that. But we're going to assume he's going to keep that. And then I'm going to come and say, what's the likelihood of Esteban also picking Sour Patch? So now what's the likelihood of you getting it? 1/4. Not only has what he wanted reduced, but also how many total has reduced. Does that make sense? So then I would do the 1/5 times the 1/4. Now what if I said, what's the probability of getting a Sour Patch and then Swedish Fish? We say 1/5 for the Sour Patch, yes? But then what is Swedish Fish? 2 out of the 4 or 1/2. The only thing that changed was the total number of items, not the total of what you want. Yeah, okay. So you always assume what you want. Oh, look at that. You always assume you get what you want the first time. All right, we're going to do one and then we're going to stop. A random number generator on a computer selects 3 integers from 1 to 20. What's the probability all 3 numbers are less than or equal to 5? So if it's a randomly generated number, are each of these events independent or dependent? Independent, right? A randomly generated number comes from a fresh set every time. So these are independent, okay? And it says that you want all 3 numbers to be less than or equal to 5. So I need to know the probability that the first one is less than 5 times the probability the second one is less than 5 times the probability the third one is less than 5. So if it's 1 to 20, how many are less than 5? 1, 2, 3, 4, right? 4 out of the 20.
Less than or equal to.
Thank you. Less than or equal to 20. So 5 out of 20. And then independent. So that is the same set again the next time. 5 out of 20. And then independent. So it's 5 out of 20 again. So it would be 1/4 times 1/4 times 1/4. 1 out of 64. Now, if the numbers 1 through 20 were in a box and you pulled one out and kept it, now my sample space is going to change each time. So if I pulled a number out the first time, it would be still 5 out of 20. But we assume that one of those is gone. So the next time it would be 4 out of 19. And we assume one of those is gone. So the next time would be 3 out of 18. Does that make sense? Yes? Okay. My advice is to